So, good morning. We will present a lecture in English, even though I think there are no. Oh yes, at least there is at least a couple of Erasmus students. Hello. So, we were considering the problem of designing a controller for a linear system in which you want to impose the closed loop poles, and you explore the fact that you know a state realization. So your compensator is made of two parts. An observer that produces an estimate of the state that I call x hat, and this observer is defined by this equation, the second equation here. What is this? This is a replica of the system driven by an output error. So you measure y, you compute what you expect y to be given your estimate of the state x hat, and this is cx hat, and you reinject this output error with a gain L. Actually, this equation is already in a way that such that we have a state realization for the observer. So I'm collecting this here all the times on x hat. So we have the state observer, and then we feed back the state observer. And this corresponds to this block diagram that you see here. So you have your plant on the top, you measure y, and y is the input to the state observer, and you output the output u, which is k minus k x hat. Now, how can we design this? We can design our controller, so the vector of gains k, assuming that we have no observer. So you design k by imposing the eigenvalues of a minus bk. And then you also design your observer assuming that you have no controller. So by imposing the poles of a minus lc. So you select L such that a minus lc has eigenvalues where you want. And typically the eigenvalues of the observer are 4 to 10 times faster, that is to say to the left, than the eigenvalues of the controller of a minus bk. And then what happens? The so-called separation theorem takes place, that is to say, the eigenvalues of this system, and you should bear in mind that this system is a 2n order system, because you have n states from the system and then states from the controller that come from the equation of the observer. So you double the order. So you have 2n poles, and the 2n poles are the poles of the controller, eigenvalues of a minus bk, and the poles of the observer, eigenvalues of a minus lc. Okay? So this is a separation theorem, and we have computed the closed loop poles and obtained this result. So we can just design the controller and the observer ignoring each other. Now, I would like to go through an example of a state feedback control system. So, and the example is a model for an inverted pendulum. Okay? Not much different from what you have in the lab. So you assume that you apply a force at the bottom, and you want to equilibrate this. Okay, so you write the nonlinear equations, And then you make an approximation that the sine of the angle of deviation with respect to the vertical is equal to the angle itself if measured in radians, because the angle is small. Okay, so this approximation is valid for small angles, and you end up with a linear state for small values of the state. So the state will be the position, so the angle, and the derivative of the angle, so the angular velocity. And your manipulated variable will be the acceleration of the bottom point. So this point here, assuming that you have here a car, and divided by L. So this acceleration is proportional to a force. Okay, according to Newton's law, this is equivalent to have a force that drives the car. So for simplicity, assume that your manipulated variable is just this u. So, and to fix ideas, we assume that we have G over L equal to 9. So G is 9.8 meters per squared second. That's the acceleration of gravity. So this is the L should be not much different from 1 meter, so a little bit more than 1 meter. Okay, so we can work with numbers. Okay, so our system, matrix A, B, C, we are measuring. We assume that we are measuring the angle. And the first thing is to design the controller. So for that, you build the matrix A minus BK for a generic K. Okay, now you compute the characteristic polynomial of this matrix A minus BK, the so-called closed loop dynamics, assuming that you have no observer. So this characteristic polynomial is here. It's a function of K1 and K2, the gains, the controller gains. And our characteristic polynomial is s squared plus 2s plus 2. That corresponds, I think it's written here. Well, it's not, but it corresponds to have poles, desired poles at -1 plus or minus j. Now, you equate the closed loop characteristic polynomial, s squared minus k2s minus 9 plus k1, with the desired characteristic polynomial alpha of s. So you get minus k2 equal to 2 and minus 9 plus k1 equal to 2. And solve it, you get k1 equal to minus 11 and k2 equal to minus 2. Okay, so this is quite straightforward. Any question? Now, what is the observer? The observer is, of course, you can write using block matrices, but you can also observe in this case, and a lot of some coefficients are 0. So the observer is a replica of the system. So you place here a replica of the system, you see. If you ignore this L1 and L2, you have a replica of the system. And then you compare what you expect the output to be, and the output should be the first component of the state, x1. So you expect y to be x1 hat, the estimate of x1. So you do this output estimation error. And you multiply this error by gains, L1 and L2, because you have two states. And you inject this error multiplied by L1 at the derivative of x1. So the derivative is just before the integrator. And to the derivative of x2, just before the integrator. Okay? So this is the structure of your observer. Now, in a practical situation, here above, this is physical. And below, this is something on your computer. Okay, so you will have some analog to digital converter connected to Y, connected to the sensor that measures the vertical angle and the deviation angle with respect to the vertical. And here you have information about your U. So probably U is something generated by software according to your controller. It's not yet done here. So you will have a DA converter at this point to apply the computed control to the system. Now, this is just a state observer. Now, what shall we do? We shall later do a feedback of these state estimates and generate U in that way. For the moment, let us start by designing L1 and L2. So to design L1 and L2, we need to design this matrix A minus LC such that it has eigenvalues in specified positions, okay? And so start by computing A minus LC for generic L, so generic L1 and L2. Then compute the dynamics of the estimation system of the observer in terms of L1 and L2, which is just a characteristic polynomial of A minus LC. And now we have to specify the dynamics of the state estimator. So we define a polynomial alpha O. I put the O to say that it is relative to the observer. Before we had an alpha C was the desired characteristic polynomial for the controller. And remember, the controller places the poles at -1 plus or minus J. And here the poles are at -4 plus or minus 4J. So 4 times away from the controller poles. And now I compare this desired characteristic polynomial with the characteristic of polynomial that I get as a function of L1 and L2, and I get equations for L1 and L2. So L1 should be 8, and L2 minus 9 should be 32. So this gives me the values of L1 and L2. Questions? And now I put everything together. So before we had the state observer. So now I pick up the estimate of x1, I multiply by k1. I pick up the estimate of x2, I multiply by k2. I sum them and generate U with a minus sign. Remember that by convention, we decided that the control was minus k x. Okay, so this is our observer. So this is our controller that should regulate the angle to 0 because nothing is coming here. Okay, and we have 2 sets of poles: the poles of A minus LC that will impose the dynamics, and the poles of A minus BK that imposes the dynamics of the angle, plus the poles associated to the observer that are faster. Let's do some simulation. So this is just the angle, and you start with the pendulum with a little bit tilted, so not in the vertical position, but pointing or deviated with respect to the vertical by an angle of 0.1 radians. And your initial estimate is 0. So the green line is a state estimate. And the blue line is the actual angle. And you see that there is an error This error oscillates because it starts by having one sign and then it has another sign. And one important thing is that this is converging. So the estimate is converging to the true angle much faster than the transient of the angle, so that you can do control properly. And this is converging to zero, so you are actually stabilizing. So you can see two things here. One that depends on the difference of the initial states. And this difference is the dynamics of the observer. It's the poles of A minus LC. And then you have a slower response, okay, that corresponds to the dynamics of A minus BK. And these are somewhat separated in time. Actually, what is different, what happens is that the poles of the observer are cancelled with the poles with some zeros. Okay, this is, I have not yet proved that. I will not prove it, but you can, if you do all the computations in a moment, I will show you how to compute the transfer function of the observer. You will see that the zeros, there are zeros that will cancel the poles of the observer. But they are there because they correspond to this fact that the state estimate approaches the true state, provided, of course, that the poles of the observer are in the negative of plane. Any question about this example?
Professor, good morning. I have a question. How would we know what would be a good error characteristic polynomial?
The error characteristic polynomial?
Yes, in the exercises we are given one. So we can aim the, so we can compute the gains of the observer. But
So
in general, in a real problem, how would we know would be a good
you mean how to decide?
REO?
How to decide?
Yes.
Okay. So I think there is a slide about that. I'm not sure. Okay. This is, there are some compromises. In the controller, well, usually you want things to be as fast as possible. So the poles both in the controller and the observer should be more to the left as you can. Now, the issue is what we mean by you can. And the limitations are, in the case of the controller, so of the eigenvalues of A minus BK, you are limited because you see that when you shift the position of the open loop poles with respect, so when the closed loop poles are much shifted, the more the closed loop poles are shifted from the open loop poles, the bigger are the gains. So you have a problem of saturation of your actuators. So your actuators do not have enough power to respond to your demand of having a very high gain. Okay, so this is a limitation. Now, the other thing is the poles of the state estimator of the observer. This is pure software, so you don't have any parts that say a valve that should open or a motor that should accelerate. So no, you don't have anything like that. It's just software, and you can have very large numbers. So mathematically, it's possible. Now, the problem is that your model is limited in precision. So your model is an approximation that holds only in the low frequency range. In the high frequency, you start having modeling errors. Also, you start having sensor noise, and these things you don't want them to be active, because I mean, they will destroy the computations that you have made. So to have robustness, you must impose a limitation. Okay. Let me give you one example, a pictorial example, no? Of a comic book, livro de quadradinhos. Okay, and this was a story of a guy who was being pursued by two Indians. He committed some infraction to the laws of the tribe, so he was being pursued. There were two Indians after him. They wanted to kill him, and he was doing all sorts of evasion maneuvers. Now, the two Indians, one of them were young Indian, so he had a very high gain, so he was very reactive. Okay, you can imagine as if you had a very high gain. So the guy who was being persecuted, he was making say things to cheat the prosecutors, and try to make them think that he was going in wrong directions, and the young Indian was going very fast in the direction that he wanted them to go. Instead, the old Indian, the other one was an old Indian, he had what we can say a low gain. So he was advancing much slower, but since he was advancing much slower, he was more prudent, so he was not eating the bait. I mean, if you use a fishing language, no, he was not misled easily by all the traps that the guy who was trying to escape, was placing in the way. Okay? Portanto, o índio novo tinha um ganho muito alto e engolia todas as armadilhas e todos os disparates, ele caía sempre nelas, e enganava sempre, ia muito rapidamente para as coisas. O índio velho andava mais devagarinho e, portanto, refletia mais e não seguia as armadilhas, e era mais prudente. Okay? So this is what happens in the design of the observers. If you have very fast observer, you are believing your model, but in high frequency, where and high frequency is amplified by high gain, then you will have a problem of fidelity of your model. Your model may not be trustworthy. So you should not believe on your model at high frequency. It can be wrong. So there is a limitation for the speed of convergence of your model. And this has an impact on the robustness of your system. Do you understand now what is the trade-off here? So it's
yes,
errors
sense.
in high frequency. Now, you can quantify them. You can quantify them, and you can quantify them. And to quantify them, you should. Okay, let me advance a little bit. Oops. Or to this slide. And this slide is something that you have learned when you were following the first course on control, okay, 2 years ago. Now, we have our plant, let's call it this GS. We have our controller, And then we have what? We have disturbances, W, and we have noise, V. And if you compute Y is a function of what? Of the reference that you want to track, R, but also of the disturbance, W, and of the sensor noise, V. Okay? And if you compute Y as a function of these quantities using block diagram, you have these quantities here. Now, what is important here is what we call the loop gain, is a product of K and G. And you must shape the loop gain. How? If you want to track the reference, Kg must be very big so that this first term should be close to 1 and Y should be close to the reference. Now, Kg should also be big if you want to be insensitive to the disturbance. So if we call it reject the disturbance. So the disturbance acts, but you want your Y to be still no matter what is the value of W. If Kg is big, then you have Kg appears in the denominator of this transfer function. So you are reducing the effect of W on Y by a factor related to Kg. Now, with the sensor noise, we have a problem because the sensor noise appears as a reference. So they misled you. And this means that Kg should be small. So what is the trick? The trick is that you use a Kg high when you have a good model and low when you have a bad model. And you can think of this sensor noise also as
part of the model.
Modeling errors, So you should have something like this, okay? So in the low frequency, where you have a good model and good sensors, your loop gain should be high. And how high, it depends on the specifications that you have imposed, for instance, on the error, on the tracking error, or on the effect of disturbances on the output. Now, in the high frequency, you should reduce the gain because you have modeling errors and you have sensor noise. Okay, so and then let me ask you: Can I say extend this boundary at high frequency? Depends on the quality of your model and the quality of your sensors. Okay, so if you have a budget to buy your sensors, that's it. But this one depends on your design. So can we extend this barrier more to the left so that we can have good tracking of the reference in a higher frequency range? So can I, for instance, instead of imposing that this is higher than this value up to this frequency, extend this limit frequency up, say, to here, and then reduce very fast the gain? Can we do that? You remember?
Yes, by introducing a 0 and then a pole.
Can we do it?
A 0 closer to the, yes, I think so.
Oh, actually not.
No?
Why? Because if you reduce very fast the gain, your phase is very much reduced, and you can become unstable. Okay, so there is a limit for stability that says that when you cross 0 dB, it must be your rate of change of the loop gain with the frequency cannot be higher than 20 dBs per decade. Okay, so there is a limit of the slope of the loop gain when you cross the 0 dBs. Okay, this is related to stability because the phase is roughly proportional to the slope. Okay, and if the slope is very is very big, so you are very much inclinated, sorry, then the phase is very small, okay? Becomes very much negative, and you can have a problem of stability according to something that you probably forgot. It's the Nyquist stability criterion, okay? So there is a limit. There are limits for this. Now, this is a general view of control design, this slide here, that applies to all design techniques that you apply, for linear systems at least. And it applies inclusive to our state feedback model. Because the state feedback model is actually, or the state feedback design is actually something in which you have a controller. It does not seem, but you have something like this diagram, okay? And I will show you in a moment that it is so. So you will have to, you will have to design your controller, and this means you are going to select your poles of the A minus BK and the eigenvalues of A minus LC, that's correct, such that you specify things like this. And if you have high frequency noise or errors, you have to check what is the barrier that you cannot cross. And this will depend, this part here of the loop gain in the high frequency will depend on L, on your choice of L, that is to say on the desired eigenvalues of A minus LC. And this part here will probably depend on the eigenvalues of A minus BK. Okay, so actually this is mixed because, but the eigenvalues of A minus BK typically tell you the bandwidth that you want to have. So the ultimate check is how are you selecting your loop gain? So you should check specifications of performance, so tracking error and disturbance rejection limits, and also your robustness specifications with respect to high frequency noise, and also stability. You have to check all these three things. Okay, this is a little bit like playing chess. Okay, usually we tend to simplify very much the problem and say, consider these eigenvalues, now design your controller such that these eigenvalues are attained. Okay, but this is just part of the story. Perhaps from a control engineering point of view, it's the least interesting thing. What is interesting is that you play with your specifications for performance and the fact that you want to have a stable controller and your specifications for robustness. Okay, and you will have to do some simulations. You will have to look at this loop gain also. Okay? You have a good opportunity of training these skills by designing your controller for the exercise in the lab, for the lab project of the pendulum. There we don't have a quantification of the error, and this year we don't have the opportunity to test on the real plant. But when you are testing on the real plant, you will see that you cannot be too much ambitious in extending, for instance, the bandwidth of your system, so in extending the frequency to which you ask your loop gain to be high. Now you are smashed. No, I spoke too much. You want to make some questions?
No, thank you, Professor. It was very, very well explained.
Okay, let me tell you one thing. So I said that When we have this stuff, let's go back to the first slide of today. When we have this stuff here, it looks a little bit strange because it's not exactly a feedback, because you have two inputs to the compensator. You have the input coming from Y and the input coming from U. So apparently, this is not a transfer function because you have two inputs and one output. But we can take advantage of the fact that U is minus kx hat to write this as a transfer function. So you have a controller that has an input Y and an output U. Okay, let's see how we can do it. So suppose that you have your process model, x naught equal as plus bu, y equal to cx. Now remember, what is the transfer function of this system from u to y? It's just c si minus a inverted b. Okay, and this is like this no matter what a, b, and c are. So let's think about the ensemble state observer controller. So you write the equation for your state observer. X hat naught equal to a minus LC x hat plus bu plus ly. Now, simply use u as minus kx hat. Okay, so rewrite this equation, and you have this pair of equations here. What is this? This is a state model for the controller, where the input is y and the output is u. You have a new A matrix, which is A minus LC minus BK, and the new B matrix, which is L, and the new C matrix, which is minus K, you see? So you can describe your controller by your state feedback controller with the observer. You can describe it as simply a state model, a linear state model with a matrix or dynamic matrix, which is A minus LC minus BK, a B matrix L, and a C matrix minus K. Okay, so if you can compute the transfer function of your system. It's simply the new C, which is minus K, the Si minus the new A, which is A minus LC minus BK inverted, and then the new B, which is L. Okay, and if you have, with this description, you have your process described by C Si minus A inverted B. That's the transfer function of your process. And then you have the transfer function of your compensator or your controller that receives the output of the process as input and generates as output the input to the process, you see? I'm spending my throat. So the store of the amount of words in my throat are becoming exhausted. Okay, so you understand this, because we tend to think, well, we have state space descriptions on one side, and we have transfer functions on the other side, but there are links. In design, the link is given by this one, so you can compute your the equivalent transfer function of your state feedback controller with an observer in this way. If I give you a state realization, if you compute K and L, then you have the compensator. If you look at the book by Franklin and Powell, he has a number of examples in which, for simple designs at least, you recover the lead and lag networks that you have you have learned how to design in the basic control course. Portanto, no livro do Franklin e do Powell há uma série de exemplos em que as especificações são feitas em termos de modelos de estado, mas ele acaba por mostrar que os controladores acabam por ser malhas de avanço e malhas de atraso exatamente iguais àquelas que estudaram na cadeira básica de controle. What I just said in Portuguese was what I said in English. Any question? There is an example here. Suppose that you have this system, which is a double integrator. So on one side you have the state description, on the other you have the transfer function description. And so you specify the desired poles for the controller, and you design the controller gains. And now you design the observer dynamics. In this case, I'm placing the observer dynamics, the poles of the observer dynamics at the same position of the poles of the controller dynamics. Okay, this is a limit case, and I get Yao. Okay, now I can compute the transfer function using exactly the previous formulas, these formulas here. Okay, I know A, I know B, I know C, I know L, and I know K. So I compute this transfer function for the compensator. Okay, so you should think the big message is that you should connect what you know about loop gain shaping that you have studied on basic course of control and state feedback. Okay, they are, we can say, the two sides of the same coin. Any question? Okay, let's move to another topic to close this chapter. And this topic is about, up to now we have been concerned with stabilizing the system. So we have an open loop stable system that has some disturbances, so some non-zero initial condition, and you want to drive the initial condition to zero faster than the natural dynamics of the system. Or you have an open loop unstable system that you want to stabilize and keep at zero. Zero, remember that zero is an equilibrium point. Okay, linear system usually is a linearization about an equilibrium point. Suppose that you have a temperature of the equilibrium of 200 degrees. A negative temperature is a little bit below 200 degrees. Okay, so because you are seeing increments. Now, up to now we have been studying the so-called regulation problem, o problema da regulação. You mean you want your state to be close to zero. Now, suppose that you want to track a reference, and this reference is non-zero. So instead of just keeping your state still, no matter what are the disturbances, you want to track a reference, and this reference can change. Okay. So we need to change our design, and we can change our design in two ways, corresponding to these circles here. You must add terms that deviate your control and possibly your state away from zero. So you can consider a matrix M times the reference, or a scalar times the reference. Okay. This M is actually a column because x hat dot is a column. Okay. R is the reference R is a scalar, so this M is a vector. Here, U is a scalar, so R is a scalar and must be a scalar. Okay? So we can have an infinite number of possibilities of designing M and N. Okay? I will discuss with you two methods to design M and N. Okay, so what is missing is the remaining infinite ones. Okay? So infinite minus 2 gives it still infinite. Is that true? There is a mathematical paradox of it's a Hilbert hotel. Okay, the Hilbert hotel has an infinite number of rooms, and all the rooms are occupied, but a new guest comes. So what do? You change the guest of room number 1 to number 2, the guest of number 2 to number 3, the guest of number 3 to number 4, and so on. So you have settled all the guests in new rooms, and there are rooms for all because it's an infinite number of rooms, and you open one place for the new guest. Okay, so we are more or less like that. So we have an infinite number of possibilities of including the reference, and we are going to study two. So there's still an infinite number that you will not know. I will tell you what is this infinite number. So let's consider these two possibilities. The first possibility is I want that my state estimator still works. I mean, the estimate of the state should still converge to the state when time goes on. So the estimation error should go to 0, no matter what is the value of R. So let's write the equation for the state estimation error. So what we do, we are going to make the difference of these two equations, because when you do it, we have an equation for x minus x hat, which is x tilde, our state estimation error. So I subtract the equations and the computation is here. I hope you believe in me, this slide is correct. And if you collect terms, then you end up with this stuff here, with this equation. Now, if you want this equation to be independent of R, of the reference, you want to ask that N and M are selected such that Bn minus M should be 0, or M should be equal to Bn. Okay? So with this design, let's rewrite our equations. Let's rewrite these equations. And remember that now you, in addition to have kx tilde, it will also have nr, apart from the minus sign that I included here. Okay? So I can write the controller equations in this way. I can write the controller equations in this way. So what does it mean in a block diagram? I rewrote here the equations. What do we have? This is an observer, as we had it before. Well, it's an observer. It's not exact. Yes, it is an observer as we had it before. Okay, generates a hex set. Then you multiply your estimate of the state by a vector k with a minus sign. And then your u is not just this term, but it also has this nr. Okay? So apart from if R is 0, you got the previous scheme that we had for driving the state to 0. But if R is non-zero, then there is this n term here. Now, I have a question to you: how to select this scalar n? What should it be? And what is its purpose? Suppose that n is equal to 1. Should y be equal to r? In steady state. Suppose that r is a constant. The reference is a constant, okay? And you design your k and your l such that everything is stable, okay? So, and the n is 1. So suppose that n is not there. So it's just a wire. Now, my question is y going in steady state? There is a transient, but this transient dies out because we have designed the system stable, asymptotically stable. Now, is y approaching r or not?
It should.
It should? You believe so? Why?
If we design the controller correctly, it should, in steady state, go to the reference.
I've selected k and l such that the eigenvalues have negative real part. And I'm just looking at the steady state. So in the steady state will be attained because the eigenvalues of A minus BC and A minus LC all have negative real part. So it's correct in this sense. Even though is y going to r, how can you check it? What type of computation would you do to check whether y is equal to r? Let me go to the whiteboard. So we have what? We have R, and then we have all that stuff. Your plant, and then your observer that receives generates x hat, multiplies by k, pi. Okay, y, let's put it here. Just to and so this is a linear system. Okay, it's a linear system. As a linear system, it has some transfer function. Let's call it G CL of S. Okay? Now, this is the reference, and you have some transient. Can you ensure that you are approaching here? So this is Y. And the red line is the reference. Can you ensure that? What does it depend on? Suppose that I give you GCL. So I give you A, B, K, and L, so you can compute GCL. So suppose that you have GCL. For Y to go to R in steady state, what must be true? What is the condition that you impose in GCL?
R different from 0,
Different from 0?
because if it doesn't know what is the reference,
So
how does it goes to the...
you say that it is enough that GCL of S is different from 0. What do you mean different from 0?
Oh, no, the R. The reference should be different from 0.
Yes, the reference is different from 0. Let's suppose that R is 5.
GCL must be equal to 1 for S equal to 1.
No, for S equal to 0.
Yeah.
Okay. So the condition is GCL of 0 must be equal to 1. Okay, that's assuming that GCL is stable, etc. We are assuming that, so the static gain must be 1. Okay, GCL of 1 is for the discrete time case, so you are confusing the discrete time case. Here we are in continuous time.
That was it. Yeah, sorry.
Okay, so everybody agrees? Now, suppose that GCL of 0 is not 1. What do? How do you modify your design so you have your reference? You have your reference. Let's put it here. And a direct way, so it goes where? So suppose that G CL of 0 is not 1. So in this case, how do you modify your design on the left, the block diagram on the left, such that Y approaches R? You must do some change, probably.
If we multiply the reference by n,
If you apply the reference by n, so you say, I put here again.
Yes, then our
N should be
our steady state should be 1 over n.
1 over n. 1 over n. So how do you design n? You want your steady state to be y equal to r. So the static gain should be the static gain from here.
Oh, everything should be 1 still.
So n should be?
I think it should be 1 over GCL of 0.
Okay. So it should be the inverse of the static gain of the red part. Okay. So this is our system. Okay. In this case, what happens? The x hat approaches x, and y approaches r. Now, do you like this system? This way, is this a good design? I mean, what are the good things and the bad things of this design?
Well, it's good that it follows the reference at least.
So the y follows the reference. Now, would you believe that this would follow the reference? You go to the lab, okay? You do your design, you know A, B, and C. You do some simulations, and Y follows the reference. Now, instead of applying your controller to a simulated model, you go to the lab and you apply to the true plant. Are you sure that Y follows the reference? There are a number of assumptions here. If you have a true system, probably you have a modeling error, don't you? You have a modeling error. If you have a modeling error, can you ensure what is the value of the static gain of the plant? Probably not. Okay, so your N, but your N depends on that. And if you have an error on GCL of 0, you will have an error in Y. Okay, so this is not robust with respect to the tracking error, for instance. Now, let's go back to basics. The first guys who talked about the feedback control, you have your plant. Okay, and they knew nothing about Laplace transforms or zeros or poles or whatever. What they were doing, they have Y, they have the reference, and then what was the idea of the basic feedback control? Look,
To follow the reference.
yes, you want Y to follow the reference. So what was the scheme, the very basic scheme of feedback control?
You just feedback Y and sum it to R.
So
The difference.
measure it, that's why it's feedback. So I subtract it,
yes.
And then I amplify it. And then I say, well, if Y is, and I get my U, no? So if Y is smaller than R, U is bigger, and this gain is such that it moves the plant so that Y increases. Okay. Then we discovered that the fact that the plant has dynamics has a lot of properties. You have instability and so on. But this is the basic idea. So compare the output with the input and amplify it. Do you think that this is what we have here on the left? So this is Stonehenge, stone, not henge, but stone age feedback. Okay, you can imagine people dressed with leather, okay, and grabbing girls by the hair and so on to the caves, and designing feedback controllers in this way. And this is modern, sophisticated feedback control. Now, if we have a modeling error, I mean, I don't even have a model. I just rely on a high gain because Y will be something which is K plant by 1 plus K plant R. If K times the transfer function of the plant is big, Y is close to R. Okay? And here, with no matter what are the errors on G, because you can control K. Now here, and you are just saying it's big. I mean, how big? 10,000, 20,000, it's big. Okay, here, all the errors that you commit in modeling, you will have a problem. So probably here, this is quite different from the state feedback. So we have a robustness in tracking. Okay, but not everything is bad here. Can you think of one good thing of our modern sophisticated feedback controller? We are estimating the state correctly. If having an estimate of the state is important, for instance, you can have an estimate of the state if you want to monitorize your system, okay? And you can use this observer to estimate the state, okay? To see whether your states, for instance, are in a safety region. So good thing, the estimate is actually approaches the true state. Bad thing, well, it became too sophisticated, so you no longer compare the output with the reference directly because you have all this stuff here. This diagram is much more involved, and as a consequence, it's not robust with respect to modeling errors. If you have a modeling error, this N knows nothing about it because this N must be precisely the inverse of the static gain. Okay, here the gain must be big. Here N must be precisely the inverse of the static gain. You see the difference? Okay, so probably we should explore other options that are closer to this old idea of having a tracking error and amplifying it. So perhaps instead we could put all this stuff here as in K. So K, instead of being just a gain, can be a frequency dependent gain, that is to say a dynamic system. Any question? So let me go back to the slides. So let's use another option, which is the first option was we want to have not to disturb the equation, the error equation. Now we do another option. We say I want to use the difference between R and Y, that is to say the tracking error E, in the controller. Okay. So I select N equal to 0 and M equals to minus L in this design. What do I get? I get this equation. So N is no longer there. So this term is no longer there. M is minus L. So this is L, Y minus R. Okay, that's minus E. So this is a state model in which E enters, E is the input, and U is the output. So this is what we want. The diagram of this model is this one. So you have the observer, and you do a feedback of U to the observer. Okay, or if you want, you can directly estimate. You implement this block, which is something with input E and output U. Okay, but what is important is that you are building the tracking error and amplifying it. Okay, so what is the good thing? This is now becomes robust with respect to the tracking error. What is the bad thing? Now the state, the state estimation error no longer converges to 0. Okay, so this X hat no longer converges to X. But what is important is that you have a compensator. So your final aim is to control the system. So if your state estimator by itself is not important, this is probably better than the other scheme. Okay? Now, these are two possibilities. Can you think of another possibility?
Can we use two observers?
Or combining the two schemes?
Yes, exactly.
Okay, so what you do for combining both schemes? You would filter R, not necessarily with just a constant. Okay, so you filter R, and you have another block here. Okay, so this is we call it a two degrees of freedom controller. So you have a filter for R, okay, and a feedback controller. And the feedback controller is giving robustness, and this filter is giving you performance. Let me give you an example. No? Suppose, think of a football team. In the football team, you have a defense, but then you have what they call the number, I think it's a number, player number 6. No? And the player number 6, his aim is to sweep and make the first line of defense to the attack. Okay, so the filter on R is the first line of attack. And then you have the defense. Okay, let me be more precise and give you an example. Suppose that you have a crane. And the crane is a car, which is my hand, and this is moving. Okay, and you have loads here. Okay, and when you move the car, the load oscillates. So you want to move your car from this point to that point without oscillations, because you want to be fast. Okay, you want to move your loads from the ship, say, to the shore, and to unload the ship very fast. Okay, but if you have no controller, what you do, you know that this is a high oscillating system. Okay, now you can apply a feedback controller, but the feedback controller, you know already that the system is highly oscillating. So when you apply the reference on the car to go from this point to this other point, you know that this is going to oscillate naturally. So what you do, you filter your reference to avoid that oscillations. Okay, that's player number 6 plane. And then your control is not perfect. Your anticipative control is not perfect. So you have this feedback controller that stabilizes the system, and it's robust with respect to tracking errors. You see? So that's the idea of the having two controllers combined. Now, how can we design these two controllers? You impose the transfer function between R and Y. Okay, and you can do that using polynomial techniques, but this is not studied here. In computer control, actually we study this in the discrete time case, but we don't study all this stuff of these controllers in much detail. Okay, so this is the other infinite number. The other infinite number of designing controllers is to have here a dynamic system in the loop and another transfer function in the reference. Okay, and design these two dynamic blocks of the controller such that in a clever way, and the clever way means stability and robustness, such that you have the designed behavior. Any question? There is still one thing that I would like you to, just a couple of slides before we end this chapter. It's the inclusion of integral effect. Okay? Sometimes we want to impose an integral effect to track a reference, for instance, in this case, or to reject a constant disturbance. So how can we track a reference? Well, how can we include an integral effect? We can add a new state. So consider this xi which is the integral of the tracking error. Okay, so if you differentiate your state xi, you get y minus r. Okay, but y is nothing more than cx. So you can augment your state model with this equation: xi dot equals to cx 0 xi. Okay, cx minus r. So you have this extra term here. And now you design your controllers taking into account that now your matrix is this augmented matrix, and that your B matrix is this augmented matrix here. So you have something which is a feedback of this augmented state. So you have your state feedback control plus something that comes from the integrating the difference between the reference and y that comes from this extra line. That's xi, the definition of xi. Okay, but bear in mind that this ki and k0 are not designed separately. Now you have to design them together and on the basis of this enlarged A matrix and this B matrix. Okay, so you should design your controller, your feedback controller, based on these two matrices. Now here I'm assuming that I have access to x and xi. When I don't have access to x, well, to xi I always have access by definition because I know r and I know y that comes from the sensor. So I only need to estimate x. If you consider the model that is this enlarged matrix and an enlarged C matrix, it is non-observable. But that is not a problem because you don't need to estimate xi. So you just need to estimate x, and for that you work with the old model. So it's not written here. So with x dot equals to ax plus bu and y equals to cx, and you estimate x. Okay, because xi you know it. So this concludes the second chapter of the course. Any question? We have time for a quick question. Okay, so if not,